Hello, everybody. Welcome to PyData Global 2024. I am so excited to introduce to you your speaker, Ian, who is just one of my favorite, very involved in PyData London, and now here, ready, enthusiastically excited to be here with you all today. A few things as attendees, we really would love if you wanted to use the chat and interact. Ian will answer questions towards the end of the presentation, so you can leave those in the chat or in the Q&A section. Both should be on the right-hand side of your screen. But I'm not going to take any time away. Thank you, Ian, for being here and giving back to the community. The floor is all yours.
Sure, it's great to be here. Thank you very much. Right, thank you very much, Tamara, and thank you, Peter, for starting off the chat. Hello, Peter. I haven't seen you in person for a little while. Good to see you're there. And with that in mind, you've got to know, as a presenter, speaking to a blue screen, in fact, staring at a camera, trying to read my slides underneath in my own room, it's pretty lonely. It'd be really nice if you could write some comments. It's always nice to know there's other people out there listening. So if you want to comment away, that'd be lovely. Who am I? What am I doing talking here? So as Tamara said, I've been involved in the scene and the community for quite a long time. Peter was talking in his keynote about the criticality of the community in our PyData world. So I'm an interim chief data scientist. I go into data science teams that are having trouble getting to success, and I help them become more successful, often by helping the business leaders around them ask better questions so we can help the smart people do smarter, better work. I've been in the field for 25 years now. I've done a lot of intellectual coding, intellectual property development and coding in the first decades of my career, and then a lot of training. I'm co-author with Misha Gorolik of High Performance Python, and the third edition of our book will come out next year, which I'm very proud of. And I finished writing the manuscript, so it's great to get past creating the new edition. I do a lot of training around doing data science successfully. I run a private data science leadership group called Rebel AI, a bunch of leaders who are all excellent data scientists getting into leadership, doing things differently so that we do better with our data science careers. And I'm a co-founder of PyData London. So we started that 10 years ago. I've been volunteering monthly for a decade now, along with a group of 20 co-organizers. We had our Christmas special last night. So we had 150 people in hedge fund man group last night celebrating 10 years or 11 years now, I think. We've got over 14,000 members in that community. So what am I talking on here? I'm not talking about strategy or coding data science. I'm talking about coding, getting LLMs to code our solutions for us. I've spent 6 months, for the fun of it, working on Kaggle's ARC AGI, the Abstraction and Reasoning Corpus Artificial General Intelligence Challenge. That challenge was put up to show us that LLMs are an evolutionary dead end, and the industry has been held back by them, and we need to go further forwards with new ideas. The philosophical question is interesting. I just love the idea that I get to challenge LLMs to go and solve these logical puzzles, which I'll show you in just a moment. And here I'm going to talk about some of my discoveries in the 6 months working on this in evenings and weekends, because I'm a slave to my ideas. Do we have the right text representation? I've got an audience question for you in this. And can we score, give feedback in a way that gets us closer to the truth? And the answer, I believe, is yes. And part of the reason I'm talking about this is because I want more collaborations around this space. I've become a little bit of an LLM addict, not a GPT addict, but just an LLM addict in general. So what is this ARC challenge? It asks the question, can an LLM reason about a novel problem that it's never seen before? This was designed by Francois Chollet. And so a training set of public data is released, and there's a private set which will never be released on the internet, so it can never be sucked into the training loops of any of the LLM vendors. And here we see some of the public data. There are 2 grids on the right-hand side with reds and blues. The left-hand one is the initial state, and afterwards there is the target state. And the question for you, here's a question for you right now. Look at those 2 grids. What is the rule that governs the transformation of the left red and blue grid to the right red and gray grid? I'll show you some more examples in just a moment. These are expressed in JSON, and the question is, can you feed these into an LLM and have it write a program or in some way solve this transformation? You give it several examples, 3 shots typically, and then you ask it to solve a hidden 4th shot. And then when it's uploaded to the Kaggle servers on an isolated environment, so none of the test data would leak out to any of the training regimes of the providers, they would see problems which they've never seen before with rules they've never seen before on these grid-like constructions. So here's a further example. Maybe you thought about the rule. You see on the left-hand side the dominant color red in both those examples. The dominant color, red in the first and dark blue in the second, maintains to the target grid, and all the other colors are wiped out. They're turned into gray. So that's kind of an interesting majority rules problem. On the right-hand side, there's a very different problem. It's a much larger grid. There's a bounding box in red and a shape. The shape has to be copied into the bounding box and expanded if necessary, and the target grid is sized to be the same size as the red grid. So there's a couple of transformations that have to occur there. And to an LLM that isn't doing vision or could be doing vision, but is seeing this novel problem, it's a hard challenge. It kind of doesn't make sense. What is this all about? But I can solve it, and I had a go. Francois Chalet says that even young children, as young as 4 or 5 years old, solve many of these problems. I tried my 4-year-old. He wasn't very good at these, but I did withhold some chocolate until he'd solved a couple. So I knew he could do a couple of them, but they're clearly quite difficult. But as a human, if I go through them, there are bits in the back of my brain where I stare at it for a moment and I think, oh, I can see the rule. Something just cogitates away and I can solve it. And that's kind of interesting. I give it to the LLM and it's not very good at this, but could we make it good? Well, potentially so. You may think some of these problems, they don't look too difficult. Some of them become very large grids and very difficult. So a large data set to feed just in a token space into an LLM. Here we get a very noisy grid with an obvious color pattern. As long as you're not colorblind, there's an obvious color pattern here. But that large noisy grid makes it really difficult for a machine to intuit what's going on, unless the human is solving the problem for it, giving it lots of hints. And the whole point of this challenge is the human doesn't solve the problem, the machine solves it itself. You can follow that arcprize.org/play, and you'll get given random problems to go and try it yourself. How have I been solving this? Well, the first version, the last 6 months worth of work, I've gone as old school as I can. I'm an author of O'Reilly's High Performance Python book, so I like to run my own code and hardware where I can. So I've got an RTX 3090 with 24 gigabytes of VRAM. It's been sitting on my desk, plugged into my laptop. That allows me to say the Llama 3.08 billion parameter model, which takes about 10 gig of the 24 gig of VRAM. And I can put in a prompt and get an answer, and kind of 20 seconds per prompt gets evaluated. It's pretty quick. One at a time, but pretty quick. If I put in the 70 billion parameter model, 40 gigabytes, that overflows the VRAM. And so some of it runs on the CPU much slower. It takes about 3 minutes for the same prompt to be evaluated, severely impacting how many experiments I can run, which is kind of an interesting trade-off. And there'll be ways to put it in the cloud and go a lot faster. But I wanted to just get a full idea of what it means to run this kind of GPU compute on a Llama-like, LLM-like problem, starting with this home setup. So what am I feeding into this LLM? I've said that there's this grid. It's a JSON-like grid, or it's a JSON grid that we are given, which can be represented in colors on screen, but really it's a JSON grid of numbers. What am I feeding into the LLM to ask it to solve this challenge? Well, here's a prompt. I've got 3 slides showing the prompt. Here's the first bit. You're a problem-solving system that can transform a geometric pattern into a target result. Before you figure out the rules, please describe what changes between the initial and the final grids. Use geometric terms. Think about relationships. I give it a couple of clues about some rules that maybe it needs, which gives it clues about this particular problem, which doesn't generalize so well, but it helps me work on this problem. So I'm kind of happy with that for this round of experimentation. So I give it this setup. Then I give it an example. On the right-hand side, you see the initial and the target grid. And so I give it this, because this is public information. We give it 3 shots of, you've got this and you want this. You've got this, you want this. You've got this, you want this. We give it those 3 examples. So here's one example laid out. The red bounding box on the left-hand side shows that initial is a grid with shape of 3 by 3, and I've got a dense grid of numbers, 222, 218, 288, representing the reds, dark blue, and the light blue. And I can write it as a JSON grid. That's how it's presented to us from Kaggle. So I get that, that representation in JSON. And then I say, well, when you've passed it through there will come out a grid on the other side, and then the reds and the greys are encoded as 222.255.255, both as a dense grid of numbers and some JSON. So that's the second part of my prompt, and I repeat this for each of the example pairs that I've got. And then I have the ask at the end. I say, right, I've given you some examples. This transformation of initial to final requires some geometric reasoning. Think, I love this anthropomorphization of use. Think, please machine, think, cogitate about what changes between initial and final to encode a transform function. Please use the following prototype function enclosed within the 3 backticks in this markdown form. And I've defined the transform function with an input and an output, and ... you fill in the bit in between. And I got this idea from reading papers on program of thoughts prompting and PAL, program aided language models, both from 2022. Really interesting papers that started this notion of explain a problem, show some code, write a prompt, maybe, write a comment in the code, and then let the machine carry on completing the rest of that paragraph, but by writing code, because it's been set up and then it has the code. Here I've changed it a little bit, but the idea is that it goes and writes this code for me. And here's the whole prompt. It's zoomed out. You can't read all of this. At the top is the setup section. You're a problem-solving machine. Here are some clues. Then I've got the example section, 3 examples showing each of the pairs, initial to final, initial, final, initial, final. And then at the bottom, the prototype transform function and the ask. Please write some interesting code for me. And so I push this into my LLM. So how am I doing that? Well, this is the big picture that I'm using. I generate this prompt. That's the prompt we've just seen for one specific problem. And I do add some specific hints for that problem, which seems to be necessary, at least with Llama 3.0. I use llama.cpp, which is a Llama runner, which runs locally on my CPU and GPU. It pushes all the work onto the GPU if it can, but otherwise it just runs it on the CPU slower, but it runs it. It pushes it out. I get a response back. The response is almost always code, unless I use a heavily quantized, so a compressed model, a heavily compressed one, I can get random rubbish back. But if I use an uncompressed model, typically I get code, and good code, which I'll show you on the next slide. And then I can say, well, let's run it. So I can run the code. I pass in that JSON string. I run it through that JSON function in a sub-process, a clean, fresh Python environment, because I've seen programs that go and rewrite the global state of my current environment, and some of them nobble my scoring function to show that they score well. They had no visibility on that, but by random chance, they nobbled the more public scoring variables I was using. So I had to then make an isolated sub-instance using joblib to run a bunch of these, evaluating them in parallel in clean, fresh environments. Often they fail. Something's wrong in the code, so I capture the exception, and then I can use that as feedback, which I'll show a bit later on. Does it work? Well, on this particular problem, if I run it 100 times, 42 out of 100 times, I get a function like what's on the right-hand side, which has a number of lines of pure Python and NumPy code, which will do the counting job and the replacement job, and it solves the problem. So kind of 40-odd% of the time, with a little bit of clue and a prompt that's kind of verbose but clear, it ends up writing the solution that I need. It does counting. There's comments in there. I didn't say write comments. It wrote its own comments. There's pretty reasonable NumPy in there. It does the correct substitution. And on the 3 test input-output pairs, it does the right job. And then on the never revealed test example that I've got in the public test set, I've got that. The LLM never sees that. I never pass that in. So I've got this 4th example pair. So I know what it is, but I never show it to the LLM. I pass the 4th example into transform as an initial. I get a generated final, and I compare it to the desired final, and I can say, you got it right, or you got it wrong. And it works, 42% of the time. That's kind of amazing. That kind of blew my mind. I mean, we know that these things can write lines of code, and we know that they're meant to be able to write lots of code for us. The fact that it could solve a geometric transform that it's never seen before, it was kind of interesting to me. You get lots of convincing weirdness coming out the other side. You get code that looks good, but it won't run. You put it inside your visual code, and then you find red underlines all over the place. Here, there's a syntax error, or lots of overfitting. It's decided these rules only apply to one of the examples, or it's got the wrong rule. It's decided it's picked up a different pattern entirely, and it's tried to solve for a very different pattern. Why am I running this so many times? Well, that came from a couple of interesting papers. More agents is all you need, and the self-consistency paper. And so these are from earlier this year and last year. The more agents is all you need paper is kind of the interesting one. If you look on the diagram in the bottom left corner, accuracy curves in GSM 8K. If we look at the blue line, that's one of the old Llama models, not Llama 3, but one of the old, I think Llama 1, 13 billion. If you ran it once repeatedly on the same problem set, it would solve that task about 35% of the time. That's the data point in the bottom left corner. If you ran it 20 times and took the majority answer, then you end up with an accuracy of about 50%. And it turns out, if you then go left, Llama 70B, a much bigger model, run once, gets an accuracy of about 50%. So lots of runs of a smaller model gives you the accuracy of a larger model run once. You run Llama 70 billion many times, and it ends up with an accuracy of about 70% on average on this ensemble majority guess, which was about at the time the accuracy of GPT 3.5 Turbo run once. And so it's kind of interesting that you run it many times and then you take an ensemble, you've got a scoring method. Here I've got a scoring method. We can get a better answer out the other side. So here's your audience question. I want you to think about this. If you want to write it in the chat, that'll be amazing, because I can see that you're out there. But if you just want to keep it in your head, that's okay, because I'll show you the answer on the next slide. What about representation? In our traditional machine learning, representation is critical. We do a lot of work on feature engineering. I've done lots of years of feature engineering, tweaking out all of the signal, and then deep learning comes along, and deep learning can tweak out its own signal in its own amazing way. But if something doesn't do that work, pulling that signal out, then you get a bad answer or no answer because the signal hasn't been revealed. What if my JSON representation that I was provided with wasn't good enough? What if that dense block of numbers that I used, the 222, 218, 288, what if that wasn't good enough? And so I tried a bunch of different representations. And here's your question. Out of these examples on screen, which one is the best? You can write it into the chat. That would be a great guess if you could do that. I'll show you the answer on the next slide. So what if it's the dense block of numbers in addition to the JSON? Or what if it's the comma separated numbers, 2 comma space 2 comma space 2? Or the quoted comma separated, or quoted with single quotes, not double quotes, or with space or without space, or maybe the Excel format that's shown down at the bottom. And there's a paper, Large Language Models Understand Layout, that talked about different ways of doing spatial reasoning on an A4 sheet of papers worth of data. And then it talked about how if they use different line separators, they get different qualities of results. So this made me start to think about, well, am I representing the problem the right way? And so, someone said, Tolly, you've said it's whatever is closest to how a machine reads data. Well, kind of true, but I think it's closer. Well, that's true. I think it's also true that it's likely to be very biased based on the training data that's been given. So it all depends on what training data has been most consumed that represents this kind of problem to give it some kind of pattern recognition ability. And I don't know what it's been trained on. So I had to go and try these different examples, much as we try different feature engineering approaches. It turns out using just JSON by itself, I get a 12% success rate. If I use JSON plus the dense number block, 222, 218, 288, that was my early local optima, 42% of the time. And all of my little tweaks after that just made it worse. I tried JSON and numbers with comma separation, 30%. And I tried a bunch of variants there, and they all got a bit worse. I tried the Excel and JSON variant, 14%. So marginally better than JSON by itself, but not really adding any additional information. But JSON and the CSV-like representation, almost like an Excel output, and maybe there are lots of Excel files with quoted numbers, so maybe that's part of the training data, 54%, much better than my previous results. And now I had a new benchmark. So I'm asking the same question, but I'm giving a different representation of that data, and it's working better. So that's kind of interesting. Representation matters, features matter. If you're doing prompt engineering, please have a think about, are you using the right representation? Could you use additional representations? Or maybe you should just change your representation and see if things get worse or maybe better. We know that different models prefer XML or JSON or YAML. Maybe some prefer a more descriptive approach or Markdown or something else. Who knows? We have to go and experiment. What if we try and add feedback? Everything so far has been a single pass. I pass in my prompt, I get an output, I evaluate it, I chuck it away, and then I try again. What if we add some feedback? What if we say, well, that didn't work. Can you try better? We know we can have a conversation. We know we can iterate here. So what does that actually mean in this context? It means that I put in that prompt, it writes a program. And then I make a new prompt where I say, this is the prompt that we had before. This is the program you wrote. That's the example on the right. You made this code block previously. It didn't work for all of the challenges. And that's all I'm giving it as feedback. I'm not saying how well it did, just it didn't work for all of them. So we have to try again. Please try again. Can it do better? And this bit blew my mind. So I start off with my 54% baseline. That's my good representation with the quoted comma separated numbers. If I do one iteration, there's no actual iteration there. It just does one pass and then it stops. That's my 54% baseline in the red outline. And then I've got I've got kind of a curve of improving quality going up to about 65% with more iterations. Each iteration is another feedback pass where I just say, this is what you tried last time. So here's the whole problem set up. And this is what you tried last time. You need to write me a transform function, do a better job. And if I do that 2 or 3 or 5 times, and I'm only giving it the last answer, not the previous set of answers, just the last answer, and I do more iterations, my average success rate goes up and up and up. But it tops out at around 65%. It doesn't get any better than that. But that kind of blew my mind. I'm just saying, here's what you gave me before. It's not good enough. Do better. I'm giving it no more guidance, and I still get a better quality program if I call it lots and lots of times. On average, I get this better quality program. What if I do more than that? What if here I say, here's the code block you made previously, and when you ran it on the first input-output pair, the first initial final grid, given the initial grid and the desired output grid, you generated this grid, which was correct. Well done. You should preserve your logic for this. But given this initial grid and this desired final grid, you made this, which was incorrect. You need to improve the transform functions. Now I'm giving it some kind of guidance. I'm not saying what it got wrong, just which inputs and outputs worked and which ones didn't, and giving it its program and then letting it decide what to do with this. And then that's the green line. The blue line is the same as I had before. The green line markedly improves. All of a sudden, I'm climbing up to 75% accuracy with 5 iterations. It kind of tops out at around 5 here. And this kind of blew my mind because more frequently my code is being generated correctly, so it finishes that cycle and starts another cycle. So I'm getting through more cycles more quickly. But here I'm still not telling it what to do next. I'm just saying this is what did work and this is what didn't work. You figure out what to do better, and it does. And this really blew my mind. This was a really lovely result. And I'm using this in some of my client work now, where I've got some way to evaluate the truth, and then I'm using it to evolve rules or code to solve their challenges in an automated fashion. But this blew my mind that this is possible. I'm automating myself out of a job, right? But I'm the one guiding the machine in how to do this, this new process. So can you give feedback and can you iterate on your problem? Because I think this is a very powerful paradigm to be thinking about. Overall, I've jumped from 12% correctness on one problem. I've tried it on several, but mainly on this one. Jumped from 12% to 75% correctness by changing the representation and by giving some useful feedback to the model. Not solving its problem for it, but just telling it where the problem lies and letting it figure out its own solution. And I reckon this idea of code-based execution, so particularly Python code-based execution, with some kind of oracle that can score whether you got something right or wrong, is a very powerful way to counteract the hallucinatory aspect of LLMs where they make up their answers. Here, it'll always write code for me and it will swear blind that the code is correct and will transform correctly until I evaluate it and say, no, you made a mistake. And it goes, oh, I made a mistake. Let me fix it for you. And so we have to have a way of evaluating to check that it got the answer right. So what are my next steps in this challenge? The solutions fixate in a really weird way. If I try one of the other smaller challenges and I give it a very easy open prompt and I don't give it any particular guidance, the A85 challenge, and that one is all about, it's a grid of numbers where the position of the numbers in each row indicates the coloring that occurs in the final result. So it's a positional problem. But it decides that the LLM Llama 3.0, 8 and 70 billion looks at that grid and says, this must be solved using the mode. I must figure out the most frequent occurrence, either of position or of the number represented. So it gets mode and then it does something with it, but it's the wrong way of looking at the problem. It's just the wrong way to solve this problem. It doesn't work. And it fixates upon it. And I have to give it some feedback and say, stop using the mode, do something else. So I have to intervene, which is not the goal of this challenge. And I've worked on some ideas around recording history. So if it does something lots of times and it keeps on getting it wrong, can I say, please don't do this again. You've done this 20 times. It doesn't work. Try something else. Try anything else. Yeah, there's a sea of wrong answers. Just don't get stuck on this wrong answer. Go fishing somewhere else. And I think it pushes it away from the bad area, but it doesn't necessarily attract it to the right area. There's only a small space of possibly good answers based on the right logical understanding. So what if we can summarize successes and produce some kind of seed bank of ideas? And so this is the last idea I was working with, a techniques library. Top right corner, there's another solution to the problem that we saw earlier on, a nice succinct short NumPy solution generated by my Llama 3 model. It uses NumPy, bin count, argmax, where to count the frequency of numbers and replace the numbers that are not dominant. And then I've gone back to the LLM and said, this code sample is interesting. Can you explain it to me in bullet points? And so it's written those bullet points where we convert the input to a NumPy array, we count the frequency, we identify the dominant number, and then we replace non-dominant numbers with a 5. And I've gone, great, that's really nice, but it's kind of verbose. Can you summarize that bullet point list of that solution into one sentence? The code applies the rule of the majority wins, where the most frequently occurring value in the input grid dominates the other values, which are replaced with a 5. And I think, great, that's kind of interesting. So now I've learned a useful pattern that maybe is a sub-pattern for other challenges. Maybe I can take this out, having done lots and lots of random runs, found some that worked, summarize the solutions that work, taken this out, and then put it into my seed bank. And maybe I could inject that into other challenges and say, here's a library, a growing library of functions that you've figured out that fit this domain, that we know work, that maybe you want to use. I haven't experimented very far with this, but I think it's a very interesting idea. So conclusions, representations matter. It blew my mind, this notion that I'm not modifying the weights of the LLM. I'm not using low rank adaptation. I'm not in any way retraining the model. I'm just changing my direction through vector space using a prompt, a static prompt. So I'm changing the representation of my problem in this static prompt, but it feels like feature engineering from classical machine learning, and I've done a decade plus of that. Scoring an iteration feels like giving some kind of surface that I'm searching through inside my traditional machine learning solutions. But here I'm doing it on my static large language model. I'm not modifying those weights in any way, but I'm giving the model a way to identify that it's going the wrong way through vector space and it should change its direction in that vector space. I think that's really interesting. I'm always interested in work collaborations. I'm super busy at the moment. I'm working in private equity on exactly this problem set. But who knows? There's always interesting things that could be happening next year. If this inspires you, if you're interested in this, if you're working on the AGI problem, I would love to hear from you. Just contact me, please. You can find me. My email address is on every slide, and I've shared these slides in the resource link here. And I've got a newsletter, which admittedly this year I've become so busy I've barely written it. But if you look at notanumber.email, you can see the past issues. I've written up some of these solutions, and I'm happy to do. I might be writing some more on this next year, and certainly working more on the AGI challenge next year, because I find it such an interesting challenge to be working on. Right, I think that's all I wanted to say. Do we have any questions? If you've got any questions or any feedback you want to share, any observations, I've given this talk, I've given a version of this talk a couple of times at my PyData London as I was working on it, and I got great feedback in the pub afterwards and new ideas from my audience. So I'm all up for hearing new ideas from you as well, if you've got them, or email me afterwards, or send me a message on LinkedIn, whatever. I'm just happy to hear your feedback. All right, I'm going to stop talking there. I think there might be a Q&A question. Let's see, where's... oh, I'm seeing claps and what's it. So there's definitely some of you out there, which is lovely. Oh, and Addy, great presentation. Ian, well, thank you very much. I wonder what will be the outcome if you had framed the problem to the LLM as a reinforcement learning solution with episodic reward feedback. I have no idea how I would phrase it as a reinforcement learning solution. Crikey. Addy, I don't know. You've totally caught me at a loss there. If you've got ideas you want to feed me afterwards, I would love to hear them. Send me an email or connect on LinkedIn. I'd love to hear that. Yeah, no, I don't know where you're going with that. Brilliant. Or write some more comments now if you want in the chat. Does anyone else have a question? Has anyone else tried the AGI challenge? I had some people in my PyData London group doing it, but only a couple out of 150 in the room on the months when I talked about it. It's particularly interesting and difficult, but very interesting challenge. All right, I'm not seeing any other questions popping up, and we're almost at time. So in that case then, thank you very much for listening. I think I have to end. Yes, I have to end this session so the next speaker has a fair chance to start. So I will wrap up here. The slides are in the resources link. Please take a look and feel very free to reach out if you'd like to chat about this. And if you're in London, come and say hello. I'd love to come see you at a future PyData London meetup. Thank you very much. It's been good being here. Thanks for having me. Bye-bye.